Just beyond the sun, a faint red star burns quietly in the dark, surrounded by mysterious worlds we may never see up close. Tonight's long, gentle journey drifts through Proxima Centauri's red skies, tidally locked horizons and cold outer worlds, all told in a calm, sleepy voice to ease the mind and slow the breath. If these cosmic sleep stories help you relax or drift off, please remember to like the video, subscribe to the channel, and gently turn on the notification bell, so future nights among the stars can find their way back. Proxima Centauri lies about 4.24 light-years from the Sun, and is the closest star beyond it. Knowing this near neighbour matters because it turns distant stars from an idea into one specific reachable point in space. By the end of this story, the nature of this dim red sun and the planets that may circle it will feel clearer and less distant. In the darkness between stars, Proxima glows like a small red ember at the edge of the sun's wider neighbourhood, faint yet steadily present. This section explains why such a small, quiet star holds an important place in ideas about the nearby region of the galaxy. A light year is the distance light travels in 1 year, and even one already marks separation far beyond any present spacecraft. 4 of those light years place Proxima outside the region. Humanity has explored directly, yet still close enough to shape maps of the local galaxy. In simple terms, Proxima Centauri is the main test example for what nearby red suns and their planets can be like. Astronomers classify Proxima as a red dwarf, a small, cool, long-lived star whose faint glow hides how much time it has to influence any close worlds. This kind of star burns hydrogen slowly, so its lifetime stretches far beyond the future of the Sun and any familiar human timescale. The result is a stable power source on cosmic timescales, where changes unfold gradually rather than in rapid, dramatic bursts. Because of this slow, steady output, a red dwarf such as Proxima helps reveal how planets behave under a star that rarely rushes through its fuel. To begin with, its low brightness means any planet receiving Earth-like warmth must orbit close, so the star would dominate the sky with red light. A planet in such an orbit moves on a tight track and circles its star in a matter of days or weeks. Earth, by contrast, traces a broad yearly path and takes 12 months to complete one loop around the Sun. This closeness to Proxima raises questions about tides and how air or oceans might move under a red glow weaker than the Sun's midday light. A key idea here is that Proxima Centauri does not just sit nearby, it changes the familiar rules of comfortable planetary distances. Proxima also belongs to the wider Alpha Centauri system, which contains 2 brighter stars that form a close pair. Proxima orbits far from them on a path that likely takes hundreds of thousands of years to complete. In everyday terms, it moves near the outer edge of that system bound by gravity, yet spending most of its time in a very quiet region of space. This arrangement shows that even a simple label such as nearest star can hide complex structure, with faint members circling far from the main concentration of light. For thinking about planets, this means any worlds around Proxima grow up in a setting shaped by their own star and the larger system's long history. Close to Proxima itself, gravity, radiation and magnetic activity combine to sculpt nearby planets into compact, fast-moving companions. Farther out, the pull from the brighter pair in Alpha Centauri may slowly adjust orbits and tilts over spans of time far beyond recorded human experience. A calm insight emerges here. The nearest star beyond the Sun is not an isolated point, but part of a pattern that stretches across space and time. Under Proxima's dim light, any planet with rock ice or cloud would see surfaces and skies tinted in shades of deep red and soft purple. Shadows would reach long, even near local midday, and details on the ground would sharpen and fade as the red star brightens and wanes. Slanting red daylight over boulders, frost or low cloud tops gives the idea of red worlds a concrete visual form the mind can hold. In that sense, Proxima turns discussion about distant planets into something that can be pictured as a landscape, not only as numbers in a list. The main thought to keep in view is that proximity makes this system the easiest place to test ideas about how red suns treat planets. Observations suggest that even from this distance, small shift in Proxima's light and motion already hint at least one planet in a close orbit. There may also be more distant companions that move slowly and are harder to measure with current instruments and observing time. These early measurements show how much information can be drawn from tiny signals when a star is both faint and close. A gentle conclusion for now is that Proxima Centauri stands as a nearby example where theory and observation meet and check each other. In that role, the closest red dwarf becomes a practical reference for understanding many others scattered through the galaxy. Next, the focus moves from the character of this star to the scale of the gap between here and there, making the distance to Proxima Centauri the next quiet step of the journey. Proxima Centauri sits just over 4 light-years away, yet that short phrase hides a distance almost beyond everyday intuition. This section gently slows that idea down and turns the gap between the Sun and its nearest stellar neighbour into something that feels concrete and calm. The key insight is simple. 4 light-years is close on a galactic map, yet still an immense journey on human timescales. To begin with, a light-year is the distance light travels in 1 year. Light from the Sun reaches Earth in about 8 minutes, crossing the space between star and planet so quickly that the delay scarcely registers. For Proxima Centauri, that same light-speed messenger needs more than 4 years to carry news from there to here. In quiet terms, the glow seen from Proxima tonight left that star when seasons on Earth had barely begun to turn a full cycle. A simple comparison helps fix the scale. The fastest probes launched away from the solar system move at tens of kilometers per second, which already represents remarkable engineering. Even at those speeds, their paths across space cover only a tiny fraction of a light-year in a human lifetime. The result is a clear sense that present spacecraft barely begin to step into the darkness between stars. On the larger map of the galaxy, however, 4 light-years place Proxima almost beside the Sun like a distant lamp at the end of the same quiet street. The local stellar neighbourhood means the small group of stars within several light-years of the Sun. In that neighbourhood, Proxima holds the record as the closest known star with the Alpha Centauri pair, next followed by other faint red dwarfs scattered through the region. This cluster of nearby suns forms a modest community of lights inside the much broader expanse of the galactic disk. A gentle summary arises here. Space between the Sun and Proxima feels empty, yet it has structure and history. Tiny grains of dust, occasional atoms of gas, and the fading influence of stellar winds still shape the medium through which any future spacecraft would move. The Sun's own outflow, called the solar wind, pushes outward and carves a bubble around the solar system. That protective region eventually thins, and beyond it the shared plasma and magnetic fields of the galaxy become the prevailing environment. In this shared space, both the Sun and Proxima send out their own streams of particles carving overlapping zones that mark the slow boundary between one stellar region and the next. A useful idea here is the local bubble, a region of thin, hot gas. Within this bubble, ancient stellar explosions have heated and thinned the interstellar material, leaving a warm cavity in which stars like the Sun and Proxima drift. The details are subtle, yet the overall effect stays simple. The nearest star does not float in perfect emptiness, but in a gentle haze shaped by long-past events. A visual anchor makes the distance easier to hold in the mind. Picture the solar system scaled down so that the distance from the Sun to Neptune fits inside a single large room. On that scale, Proxima Centauri would lie far beyond the building many city blocks away, still counted as a close neighbour, only because the galaxy itself stretches over immense spans. Another image is a calm ocean at night. The Sun is a bright ship's lantern, and Proxima is a dim red light on a second vessel, several long crossings away over open water. The ocean itself appears empty in the dark, yet currents, waves, and drifting particles quietly structure its depths. The space between the Sun and Proxima shares that same quiet complexity. For long-term thinking about exploration, the distance to Proxima becomes a benchmark. Any serious plan for interstellar travel measures itself against those 4 light-years. At sublight speeds that remain safely within physical limits, travel times still run to decades or even centuries. This does not make the journey impossible. Instead, it frames it as a project that unfolds over many human generations. A calm sentence captures the lesson. 4 light-years is close enough to imagine but far enough to demand patience. The layout of the local neighbourhood also matters for ideas about communication and observation. Signals sent as radio waves or focused light still move at light speed, so messages to a future probe near Proxima would need years to arrive. Replies would require another 4-year wait, turning any conversation into a slow exchange of carefully planned statements. This delay encourages designs that emphasize autonomy, reliability, and quiet endurance. The Sun and Proxima, along with a few nearby red dwarfs and sun-like stars, form a small island of light within this slow dialogue. Next, attention turns from the scale of the gap between these stars to the special structure of the Alpha Centauri system itself, where Proxima traces a distant patient orbit around a brighter central pair. Proxima Centauri does not drift alone in space. It belongs to the Alpha Centauri system, a small family of stars moving together through the local region of the galaxy. The core idea in this section is gentle and clear. The Sun has neighbours, and the nearest of those neighbours is itself part of a deeper structure where 3 stars share one broad gravitational stage. Alpha Centauri A and Alpha Centauri B form the bright central pair of this system. They are both sun-like stars orbiting one another on a path that carries them closer together and farther apart over decades. Seen from a distance, they resemble a single point of light that slowly shifts and circles, bound by gravity in a long, stable dance. Around this close pair, far away on the outskirts, Proxima Centauri follows its own very wide orbit. Proxima is much fainter and smaller than the central pair. From the point of view of Alpha Centauri A and B, it is an almost invisible companion. Yet gravity still links them. The combined mass of the central pair creates a deep gravity, well, a shared region where their pull dominates over the surrounding galaxy. Proxima moves within that well. Its path likely takes hundreds of thousands of years to complete. The enormous loop carries it far from the central pair, and then slowly back again. A single journey of Proxima around Alpha Centauri A and B lasts far longer than the entire span of human civilization. The result is a system that feels both tightly bound and gently spread out. Close in, the double star orbits quickly enough to change angles over a human lifetime. Far out, Proxima drifts with a pace set by the mass at the centre and the empty distances between. A helpful mental picture is a deep valley with 2 bright campfires near the middle, and a smaller red lantern hung on a distant ridge. The lantern glows faintly and moves slowly, yet it still belongs to the same valley, and never fully escapes its shape. In this shared valley, planets and debris experience not just one star, but the combined influence of all 3. Proxima's own planets, if they formed in place, grow up under its gravity and light, while also feeling the distant tug of the central pair. Over millions or billions of years, that distant pull can gently adjust orbits' tilts and the shapes of comet paths. The Alpha Centauri system as a whole becomes a gravitational island. Inside its boundaries, stars, planets, and smaller bodies move mainly in response to one another. Outside it, the broader tide of the galaxy takes over. A calm insight emerges here. When discussing Proxima's planets, it is rarely enough to think of a single star and a single world. The larger family matters. The central pair may never loom large in the skies of Proxima's close-in planets, yet their presence shapes the long-term story of how the system evolves. Over very long timescales, passing stars and the slow pull of the Milky Way may stretch or tilt Proxima's wide orbit. Sometimes it may wander a little closer to the central pair, sometimes a little farther out. Each slow adjustment slightly changes the background against which its planets move. In this way, even a world with a short year and a quick day-night rhythm can be part of an extremely slow, multi-star pattern. A second visual anchor helps fix the structure. Imagine a calm, dark sea with two bright lighthouses near the centre and a much smaller red beacon tracing a wide circle far offshore. Ships near the lighthouses feel their light strongly and use it to steer. Vessels near the red beacon still belong to the same harbour, even if they see the central lights as distant points close to the horizon. Likewise, any observers on a planet orbiting Proxima would live in a local environment dominated by a dim red sun. The deeper gravitational story still links them to the brighter pair. That pair shines from many trillions of kilometres away. For the broader study of nearby stars, Alpha Centauri shows that multiple star systems are common, and that planets can exist in such complex environments. This matters because many stars in the galaxy are not alone. Understanding how planets behave in a triple system near the Sun helps refine ideas about planets in other multi-star systems farther away. Quietly, the nearest stellar neighbour teaches that even familiar words like neighbour and system can hide rich layered structures. For ideas about habitable zones, this layered structure matters because it sets the long background conditions in which climates may slowly change. Planetary orbits do not evolve in isolation, but within this shared gravitational field that responds to the galaxy around it. Recognizing that slow framework keeps expectations about red worlds patient, measured, and quietly realistic. As the narrative continues, attention moves inward from this wide three-star arrangement to the detailed character of Proxima itself as a red dwarf. The next part focuses on its small size, low light, and extraordinary lifetime. Proxima Centauri is a red dwarf star, small, cool, and faint compared to the Sun. The gentle idea at the heart of this section is that its modest size and low brightness are not weaknesses, but the reason for an extraordinarily long life. Proxima holds only a fraction of the Sun's mass, yet it burns its fuel so slowly that its lifetime stretches far beyond the age of the universe so far. In plain terms, this nearest star beyond the Sun is built for endurance rather than for brilliance. A red dwarf is a low-mass star with a cool surface and a dim output of light. Proxima's diameter is only a little larger than a gas giant planet, and it shines with a glow that from a distance barely rises above the background sky. If the Sun were a bright bonfire in a winter field, Proxima would be a small ember held in a pair of careful hands. That small ember, however, is steady. It radiates heat and light at a rate that allows its fuel to last for hundreds of billions, even trillions of years. The key physical idea is simple. A smaller star has weaker gravity at its surface and cooler outer layers so it does not waste energy by shining intensely. Hydrogen in its interior is consumed at a slow, controlled pace. The result is a calm, almost unhurried fusion engine. each unit of fuel stretched out over a far longer time than in a larger, hotter star. Inside Proxima, the material does not separate into sharply different layers as in the Sun. Instead, the star is fully convective. That phrase means the gas inside is stirred from core to surface and back again like water in a pot kept just at a simmer. Hot material rises, cools and sinks, carrying energy outward in a steady circulation. A short definition helps. Convection is the transport of heat by moving material, not just by radiation. This deep mixing ensures that hydrogen fuel from outer regions eventually travels inward to the core where fusion can continue. In a larger star, some fuel may remain in outer layers unused. In Proxima, nearly all hydrogen becomes available over time. This efficient use of fuel is the central reason its life is so long. A slow, gentle dynamic emerges. The star's faint glow reflects not weakness but thrift. A visual anchor can make this easier to hold in the mind. Picture two lamps in a quiet room. One shines very brightly but drains its oil quickly. The other glows softly, almost modestly, and barely sips at its reservoir. Long after the first lamp has sputtered and gone dark, the second quietly continues to shine. Proxima belongs firmly with the second lamp. Its soft red light is the mark of a star that plans to remain present for an immense stretch of cosmic time. This extreme longevity has deep consequences for any worlds that orbit nearby. Around a star like the Sun, the habitable zone slowly moves outward as the star brightens over billions of years. Planets in that region do not keep constant conditions forever. Around a red dwarf such as Proxima, changes in brightness happen far more slowly. A planet that sits in a temperate orbit may remain there for time spans that exceed the entire current age of the universe many times over. A quiet summary follows from this. Proxima Centauri offers a natural laboratory for studying what long-term stability under a faint star might mean. Its small size also affects how its light feels. The star's surface temperature is lower than the Sun's, so most of its glow comes in red and infrared wavelengths. For any nearby world, daylight would have a reddish tint, and warmth would arrive more through invisible infrared than through white light. Under such a skyrock's dust clouds and ice would take on deep muted tones. Shadows would be soft and long even when the star stands high in the sky. This visual scene, a landscape bathed in warm red twilight, becomes the natural backdrop for thinking about Proxima's potential planets. The star's faintness also means that any habitable zone lies close in at a small fraction of Earth's distance from the Sun. Planets in that region feel the star's gravity strongly and orbit in short periods, completing a year in days or weeks. Yet through all those fast orbits, the star itself changes very little. It keeps its mass, its cool surface, and its slow energy flow. The long-term rhythm is stable even if short bursts of activity such as flares can disturb the calm for a while. On human timescales, Proxima's overall brightness will not noticeably shift. On geological timescales, it will still be on the same slow-burning track. Only when the galaxy itself has aged far beyond its present state will Proxima begin to move toward the later stages of its evolution. In this way, the nearest red dwarf star becomes a symbol of continuity. When the Sun has long finished its main phase and changed into a very different object, Proxima will still be in the quiet middle stretch of its life. For thoughts about habitability, this opens the possibility that red worlds around small stars could exist and evolve for periods far longer than Earth has been present. A gentle conclusion closes the section. Proxima Centauri, with its small size, faint light and astonishing lifetime, is not just a nearby star. It is an example of cosmic patience, a long-lived ember that may watch over its planets for ages to come. Next, the focus turns from this slow, enduring heart to the more restless side of Proxima's nature, where sudden flares and bursts of radiation disturb the surrounding space. Proxima Centauri may be small and faint, but its surface is restless. This section focuses on its flares' sudden releases of energy that brighten the star and flood nearby space with particles and radiation. The central idea is that Proxima's gentle red glow hides a dynamic, stormy outer atmosphere that shapes the environment of any close worlds. A flare is a rapid burst of light and charged particles from a star's outer layers. In Proxima, these events can increase brightness many times for a short period before fading back to normal. The star's magnetic field becomes twisted and stressed by the motion of hot gas below the surface. When those stressed lines suddenly snap and reconnect, energy rushes outward as a flare. A short definition helps here. Magnetic field lines are invisible paths that guide charged particles. Around Proxima, those paths wrap and coil through the star's atmosphere, storing energy, until sudden changes force them to rearrange. The result is a series of bursts that mark Proxima as a classic flare star, a red dwarf known for frequent and sometimes powerful outbursts. Even in quiet phases, Proxima sends out a steady wind of particles and radiation. When a flare erupts, that steady flow briefly becomes a storm. For any nearby planet, especially one in a close orbit, these storms can dominate the local space weather. Space weather is the changing flow of particles and fields around a star. Under strong flares, high-energy radiation can stream toward a planet's upper atmosphere. Over long timescales, repeated exposure may heat and erode the outer layers of gas. If a planet has a magnetic field, it can deflect some of this incoming flow and steer charged particles toward its poles. If it lacks such protection, the energy can reach deeper and begin to strip away lighter molecules. A calm insight arises here. Proxima's flares are not a single dramatic event, but a long-repeating influence that slowly shapes the fate of nearby air and water. On short timescales, a flare might brighten the sky on a close planet's dayside. The landscape would briefly lie under a stronger red glow, with shadows sharpening and colours deepening for minutes or hours. In higher energy events, invisible ultraviolet and X-ray light would spike far more strongly than the visible brightness suggests. Over many years, that deeper unseen part of the spectrum matters more than the brief visual flash. The main metaphor for this section is simple. Proxima behaves like a small lantern that occasionally flares into a sudden storm, sending gusts of light and particles sweeping through its compact system. A supporting image can be imagined as distant lightning flickering over a dark sea, each flash short yet part of a long repeating pattern of weather. For the planets, this pattern becomes a background rhythm. Between flares, conditions may settle into relative calm with a stable faint red sun and gentle particle wind. During active periods, strong storms could arrive, often leaving little time for atmospheres to recover fully. Whether a particular world around Proxima can hold on to its air depends on mass composition and any magnetic shield. A heavier planet with a dense atmosphere might endure repeated flares and still keep thick layers of gas. A smaller world with thin air could lose much of its outer envelope over time. In both cases, the star's behavior sets the pace of change. This makes Proxima Centauri an important example of how stellar activity influences habitability. A calm lesson appears here. Living close to a red dwarf does not guarantee a peaceful climate, even when the average energy from the star seems comfortable. The story of potential habitability around Proxima is written partly in these sudden bursts. From a broader view, flares also provide information. They reveal the strength of the star's magnetic field, its rotation, and the depth of its convective motions. Each outburst carries clues about processes hidden below the visible surface. Careful monitoring of Proxima's flares over many years allows patterns to emerge. Some periods may show frequent small events, others rare but powerful ones. Together they build a picture of a star whose outer layers are in constant motion. In quiet, slow language, it becomes clear that any planet close to Proxima lives under both a faint sun and an active sky. In such a system, the main question goes beyond simple distance for liquid water. It also asks whether a world can withstand or adapt to long ages of magnetic storms. As the narrative moves forward, the focus shifts from the star's changing moods to the layout of its planetary system. Close-in orbits and compact paths slowly reveal how these red worlds circle their active sun. This contrast between gentle average light and sudden sharp bursts defines the character of Proxima's surroundings. It sets a quiet tension that any long-lived atmosphere or ocean must learn to endure. Proxima Centauri hosts a compact planetary system where known and suspected worlds circle close to a faint red sun. The main idea in this section is that these orbits occupy a very small region of space compared to the solar system, yet they contain enough variety to hint at a rich, dynamical story. At least one planet, Proxima Centauri b, is confirmed, and others often named Proxima c and Proxima d appear as strong candidates. Together they form a miniature planetary family, all living deep inside the distance where Earth travels around the Sun. A planet is a body massive enough for its own gravity to pull it into a rounded shape and clear most nearby debris. In the Proxima system, such bodies move along paths that hug their parent star at close range. Proxima b orbits in just a small fraction of the distance between Earth and the Sun, completing a year in days instead of months. Proxima d, if present, lies even closer, encircling the star on a very tight track. Proxima c, by contrast, appears to follow a wider, slower path still close by solar system standards, but more distant than its inner siblings. In simple terms, all of these worlds fit well inside the orbit of Mercury, if they were placed around the Sun. A quiet payoff appears here. The nearest planetary system known is small, dense, and gathered near its star like a cluster of marbles arranged tightly around a dim candle. The structure of their orbits is measured by tracing tiny shifts in Proxima's light and motion. As each planet moves around the star, its gravity tugs slightly on Proxima, causing regular patterns in the way the star approaches or recedes from observers far away. This method, often called radial velocity, reveals unseen worlds through timing and repetition. A short definition keeps it clear. Radial velocity is the change in a star's speed toward or away from the observer. In the calm language of this section, these small tugs are like faint pulses in the star's heartbeat, each one marking a planet's steady passage along its orbit. For Proxima b, those pulses repeat on a short cycle, signaling a compact orbit in a region where starlight is still strong enough to allow temperate conditions in principle. Proxima d, if it exists, produces an even shorter cycle, suggesting a very tight hot path close to the star. Proxima c leads to a slower rhythm, hinting at a larger orbit where light from the red dwarf is weaker and the environment colder. The overall picture is a tiered system with quick, close-in worlds and a more distant companion, all under the influence of the same red sun. A visual anchor helps fix this architecture in the mind. Imagine a small dim lamp in the center of a dark room. Very near the lamp, two stones swing on short strings, tracing quick circles in the warmest glow. Farther out, a third stone moves on a longer string, completing its loop more slowly in cooler, dimmer light. In the Proxima system, planets replace stones and orbits replace strings, but the layered pattern remains. This compactness matters for stability. When planets orbit close together, their gravity can nudge one another over long spans of time, changing eccentricities, tilts, and even the orientation of orbits. In Proxima's case, the low mass of the star means that planetary masses represent a slightly larger fraction of the total system, so their mutual influence matters more. A calm insight follows. Even tiny worlds can shape each other's paths when they share such a tight, confined space. Over millions of years, resonances may develop where orbital periods settle into simple ratios. In such cases, one planet completes, for example, 2 orbits, while another completes 1. Resonance is a pattern in which repeated gravitational tugs line up, amplifying their effect. This gentle locking can help stabilize orbits, or in some cases slowly stretch them into more elongated shapes. Under Proxima's flaring sky, these orbital patterns decide how a planet's distance from the star varies, and how evenly its surface receives energy. For any world near the so-called habitable zone, small changes in orbit may tip climates toward warmer or colder states. The key lesson is that architecture is destiny. The way planets share space around Proxima Centauri sets the stage for everything that follows, from tides and seasons to the survival of atmospheres. In this nearest planetary system, the architecture is compact, efficient, and deeply shaped by the presence of a small but active red sun. As the narrative continues, the focus narrows from the overall layout of these orbits to the special position of Proxima b, the world that sits close to the calculated habitable zone, and becomes the main example of a potentially temperate red world. Proxima Centauri b sits in a region often called the habitable zone. Around its small red star, a band where temperatures could permit liquid water under the right conditions. A world that lies in a habitable zone is not guaranteed to be comfortable or alive, but it receives a level of starlight that makes liquid water at least possible in principle. Habitable zone means the distance range where surface water can remain liquid, over long timescales assuming an atmosphere. Around a faint red dwarf like Proxima, this zone huddles close to the star, much nearer than Earth stands from the Sun. Proxima b traces its orbit within this narrow band, completing a short year in only a handful of days or weeks. The result is a planet that always feels its star very near in the sky, even though the star itself is small and dim. In simple terms, Proxima b is an example of a nearby world that meets the first requirement for potential habitability, the right average distance, while leaving many other questions open. To begin with, the amount of light falling on Proxima b appears similar to or slightly lower than what Earth receives from the Sun. If the planet has a rocky surface and a suitable atmosphere, its temperatures could fall into ranges where water stays liquid, at least in some regions. If its air is too thin, too thick, or composed of very different gases, the surface could instead be frozen solid or wrapped in crushing heat. This same distance that looks gentle on paper can lead to very different climates depending on details that remain unknown. Being in the habitable zone is like standing in a gentle band of light on a wide, dim stage. What matters next is clothing shelter and local weather. Because Proxima is a cool red dwarf, the quality of its light differs from sunlight. Much of the energy comes in red and infrared wavelengths, so a possible sky over Proxima b would be richer in warm tones than in bright white. Under that light ice and cloud tops could glow faintly pink, while rock and soil reflect deep reds and browns. A landscape on Proxima b, if it has one, would lie under a small reddish sun that never blazes like midday on Earth, even at its brightest. The habitable zone is also shaped by time. Over very long spans, stars gradually change their brightness. Proxima's slow evolution means its habitable zone moves outward, only gradually giving planets within it a long window of relatively stable conditions. Yet the same star that offers stability in average brightness also sends out strong flares and particle storms. Those outbursts can erode atmospheres or strip away protective layers, especially on planets orbiting close in. Atmospheric escape is the process by which fast-moving particles and heated gas drift or are blown away into space. Over many millions of years, this process can thin or even remove an atmosphere if it is not replenished. Whether Proxima b keeps its air depends on its mass composition and any magnetic field it may hold. A stronger gravity and dense gases could help trap heat and resist erosion, while a global magnetic field could deflect some high-energy particles away from the upper layers of air. In a calm sentence, the habitable zone sets the stage, but air and shielding decide how the play unfolds. Tidal forces likely play a role as well, because Proxima b orbits so close to its star gravity may have slowed its rotation until it keeps one hemisphere always facing Proxima, a state called tidal locking. Tidal locking is when a world shows the same side to its star each orbit. In that case, the day side receives constant light, and the night side endless darkness. Without an atmosphere, the day side could bake while the night side freezes beneath a permanent sky of stars. With a thick enough atmosphere or even oceans, winds and currents might redistribute heat, softening the extremes. A narrow ring around the planet, the twilight zone between day and night, could then hold more gentle temperatures. This narrow band circling the terminator line becomes an appealing place to imagine liquid water cloud decks, and perhaps stable climates under a red low sun. Proxima b therefore sits at the quiet center of many questions. It is close enough and receives enough energy to be counted as a potentially temperate red world, yet everything that truly defines habitability remains uncertain. For nearby stars across the galaxy, Proxima b acts as a reference point showing how a planet can occupy the right orbital zone, while still facing challenges from stellar activity and tidal effects. The phrase habitable zone turns out to be a starting point rather than a final label. In its tight orbit around a dim red star, Proxima b shows how delicate and complex that starting point can be. Next, attention turns more fully to the special geometry of tidal locking, and to the imagined appearance of its dayside-night side, and the dim circling line of permanent sunset between them. Proxima Centauri b, or a similar close-in world, likely turns the same face toward its star. This creates a permanent day side and a permanent night side. This section explores how that tidal locking shapes landscapes, skies, and possible climates under a small red sun. The key idea is gentle. One hemisphere lives in endless daylight, one in endless darkness, and between them lies a circling band of perpetual twilight called the terminator. Tidal locking happens when a planet's rotation period matches its orbital period, so one side always faces the star. Around Proxima Centauri, the effect becomes stronger because habitable zone orbits lie so close to the star. Over time, gravity stretches the planet slightly and slows its spin until rotation and revolution fall into step. Once this state is reached, the day side and night side stop trading places. The consequence is a world where direction and time become deeply linked to light. On the day side, Proxima would hang in nearly the same place in the sky, glowing red and constant. Its light would gently wax and wane as the planet moves along an oval orbit, but midday would never race across the sky. Under this fixed star, any atmosphere would form a rising column of warm air near the substellar point beneath the star. Air heated, there would rise flow outward at high altitude cool, and then sink again closer to the terminator and night side. The result is a slow, global circulation pattern, like a steady breath that carries heat away from the day side. A quiet image helps fix this pattern. The planet behaves like a shallow rotating bowl of air warmed at its center and cooled around its rim. On solid ground beneath the substellar point surfaces could glow with deep red light, perhaps bright enough for soft shadows but rarely harsh. Rock dust or cloud would be tinted in warm colors, and any standing water would reflect a dim crimson disk rather than a white sun. Farther away from that center, the star would sit lower in the sky, turning day into an extended afternoon that lasts without end. The night side tells a different story. In permanent darkness, the sky would hold only distant stars. Proxima itself would never rise. Without an atmosphere, this hemisphere would freeze hard, with temperatures plunging until only solid ice and rock remain. With an atmosphere and perhaps oceans, the night side might still be cold, yet winds and currents would carry heat from the bright hemisphere. Dense air could spill over the terminator and glide into darkness, where it would slowly cool and sink. Over years, thick ice sheets might grow in shadowed basins, while higher ground sees dry, frigid deserts lit only by starlight and occasional auroras. The terminator zone forms a narrow ring between these extremes. Here Proxima would hover near the horizon, casting a permanent red glow along the edge of the sky. Landscapes in this band would live in an unending sunset or sunrise, where shadows always lean and colours remain muted and soft. If an atmosphere transports enough heat, temperatures along this ring might stay moderate, neither searing nor deeply frozen. A calm insight appears here. For a tidally locked world, the most gentle regions may not be at the centre of the dayside, but in this eternal twilight. Oceans, if present, would join the global redistribution of heat. Warm dayside waters could flow toward the terminator, release energy to the air, and then sink as they cool. Over time, this slow cycle might smooth temperature differences and prevent the night side from reaching the coldest possible values. Sea ice could form where waters approach darkness, forming bright patches that reflect faint starlight and help regulate the climate. In this way, the combination of air and water turns a stark pattern of light and dark into a graded environment. Flares from Proxima would add a changing layer to this picture. On the day side, a large flare would briefly brighten the sky and strengthen high-energy radiation. On the night side, only charged particles guided by magnetic fields would signal the storm, perhaps igniting auroras along magnetic latitudes. In the terminator band, red daylight would deepen or flicker as the star's output shifts. Yet even with these bursts, the basic structure of permanent day, permanent night, and circling twilight would remain. For nearby red worlds, this geometry of light becomes a common expectation. Many close-in planets around red dwarfs likely share similar locked states. Proxima's system simply offers the closest example, where orbits and star activity together guide climate models of how such a world might behave. In gentle terms, tidal locking does not condemn a planet to a single extreme. It rearranges light and heat into a pattern that favours rings and gradients, rather than familiar cycles of sunrise and sunset. As the journey continues, attention turns from this surface geometry and circulation to the fate of atmospheres under Proxima's flares, winds, and magnetic storms. The next step is to consider how well any red world can hold on to its precious air. Proxima Centauri's close-in planets live under a constant contest between air and star. This section considers how atmospheres might survive change or disappear under flares, winds, and radiation. The central idea is gentle and clear. A planet near Proxima keeps its air only if gravity chemistry and magnetic protection together can outrun the energy coming from its active red sun. Atmosphere here simply means the layer of gas bound above a planet's surface. Gas molecules collide and absorb starlight, then radiate energy away. When starlight is strong in energetic wavelengths, Some molecules gain enough speed to escape into space. Much of Proxima's output arrives as red and infrared light, but its flares add surges of high-energy ultraviolet and charged particles. These bursts heat the upper layers of any atmosphere and can drive gas upward. High above the surface lies a region where gas becomes thin and partly stripped of electrons. Ionization is the process of removing electrons from atoms or molecules. Ionized gas responds strongly to magnetic fields and stellar winds, forming tails and streams that stretch away into space. Over millions of years, this slow leakage can thin an atmosphere until only heavier gases or lower layers remain. A quiet summary forms here. Under Proxima's storms, air is not a given. It is a long negotiation between escape and retention. Stellar wind is the steady flow of charged particles streaming out from a star. Proxima's wind, strengthened by frequent flares, pushes against planetary atmospheres in a very diffuse invisible flow. If a planet has no magnetic field, the wind can connect directly to its upper layers. It then carries particles away along open field lines shaped by the star. If a global magnetic field exists, it can carve out a protected cavity around the planet called a magnetosphere. A magnetosphere is a region where a planet's magnetic field dominates the motion of charged particles. Inside this zone, most of the stellar wind is deflected around the planet and atmosphere loss slows. Some particles still spiral down toward magnetic poles, where they may trigger auroras that shimmer above dark skies. This protective shell acts as a flexible shield, not a solid wall bending in and out as the wind strengthens or weakens. The main metaphor in this section is that an atmosphere around a Proxima world behaves like a delicate shell facing a restless sea. Waves of particles and radiation rise and fall, sometimes gently, sometimes in sharp storms. The shell can endure if it is thick enough, heavy enough, or continually repaired from below. Volcanic outgassing, for example, can supply new gas to replace losses, while surface reservoirs of ice can release vapor when warmed. Over long spans, the balance between supply and loss shapes whether a planet remains wrapped in air. It may instead wear only a thin veil, or end as a bare rock. For a close-in world, the day-side and night-side may share different roles. The day-side upper atmosphere absorbs most of the high-energy light and particles, heating and expanding outward. The night-side, shielded from direct starlight, cools and contracts, drawing some gas back. Winds circle the planet, carrying heat and material between day and night. If circulation is strong, the whole atmosphere behaves as one connected system. If circulation is weak, the day side may puff up while the night side slowly thins. A secondary visual image may help. Auroras could hang above the dark hemisphere in gentle glowing curtains, as particles guided by magnetic fields meet the upper air. Beneath those lights, cold surfaces and quiet landscapes would feel the star only indirectly through the slow breathing of air and occasional tremors of distant flares. The fate of liquid water depends strongly on these processes. Where pressure and temperature stay within gentle bounds, water can pool in lakes or oceans, feeding clouds and rain. If pressure drops too low, water boils away into space, or freezes into hard ice that never melts. If greenhouse gases become abundant, they may trap heat and push temperatures upward, turning a mild world into a hot, dense environment. The same star that offers long-term stability and brightness can therefore lead to very different outcomes for its planets. A calm conclusion emerges. Around Proxima Centauri, atmospheres are both fragile and resilient, able to survive for long ages, only when many small factors align. Gravity, magnetic fields, volcanic activity, and stellar behavior together decide whether a red world keeps its air. These same rules extend outward to colder planets on wider orbits, linking the story of inner and outer worlds in one continuous chain of causes. In the nearest planetary system, these quiet struggles between loss and renewal unfold out of sight, leaving only subtle signals in starlight for distant observers. As the journey continues outward, attention turns away from these close-in, strongly heated planets to the colder outer companions. Their thin sunlight and long orbits create a very different kind of red world. Proxima Centauri's outer companions, usually called Proxima C, and Proxima D in current models move through colder, more spacious orbits than the tight paths of the inner worlds. This section lingers on those distant planets as examples of cold red worlds shaped by a faint star that never gives them strong daylight. The core idea is that distance and dim light can produce landscapes very different from the temperate possibilities near the habitable zone, yet still rich in quiet structure. At these greater separations, the energy from Proxima arrives as a soft trickle rather than a steady warmth. The star shrinks to a deeper ember in the sky, more like a bright planetary disk than a blazing sun. Surfaces on such worlds receive so little light that daylight may resemble a red twilight even at local noon. If Proxima C is a larger, perhaps icy or gaseous planet, it could be wrapped in thick clouds and deep cold air, while Proxima D, if real and more compact, might follow a path that grazes the boundary between inner and outer regimes. Both examples frame the range of climates that can arise around a red dwarf once the distance from the star grows. The nearest planetary system contains not only one candidate temperate world, but also colder relatives that extend its story outward into darker space. On a cold red world, temperatures at the cloud tops or surface sit far below the freezing point of water. Frozen gases and ices may dominate. Nitrogen, carbon dioxide, or more exotic compounds can settle as frosts and layers. If a thick atmosphere exists, internal heat from the planet's formation, and slow contraction can keep deeper layers relatively warm. This creates a separation between an icy outer shell and a more active hidden interior. In such cases, surface cold does not mean complete planetary stillness. Winds still blow, driven by small temperature differences and gentle rotation. Clouds form where rising gas cools, folding into bands or patches that drift around the globe. On Proxima C, if it is similar to a super-Earth or mini-Neptune, these clouds might reflect much of the dim red light, making the planet bright against the dark. A single main metaphor captures this state. These outer planets are like far-off islands lit only by a faint red harbour lamp, where weather moves slowly and shadows stretch endlessly. The relative isolation of these worlds has another consequence. Flares from Proxima still reach them, but the intensity of high-energy radiation decreases with distance. Their upper atmospheres feel a softer, more filtered version of the storms that strike the inner planets. Over long time scales, this gentler environment may allow fragile molecules to survive more easily in cold sheltered layers. If subsurface oceans exist beneath ice shells, they could remain almost entirely shielded from direct stellar activity, warmed instead by internal heat and slow radioactive decay in the core. In that sense, habitability in the outer system, if it arises at all, would belong more to deep dark oceans than to open skies. Around a small star, life-friendly conditions, if they exist, may hide in depth, rather than on exposed surfaces. Orbital motion also shapes the character of these red worlds. Proxima C on a wider orbit moves more slowly and experiences seasons spread over long intervals if its axis is tilted. Proxima D with a closer path might see shorter cycles, or become tidally locked like the inner planets, depending on its distance and history. Eccentric orbits slightly stretched into ovals would cause these planets to drift closer to, and farther from Proxima during each revolution. At closest approach, they would receive more light and warmth. At the farthest point, they would sink deeper into cold. Even small changes in distance can influence the build-up or retreat of ice over immense spans of time. Imagine a dim red lantern at the centre of a wide, snow-covered plain. Near the lantern, frost glows weakly. Farther away, ice thickens and darkens, shaped by rare, distant glimmers of light. Proxima's outer planets inhabit that far plain, guided more by their own internal heat and slow orbital rhythm than by any strong external glow. For astronomers, these cold companions matter because they complete the picture of the nearest system. They show that even around a small star, planetary diversity can be large, from tight rocky worlds to wide, cold giants. Measurements of their masses and orbits feed models of how the Proxima system formed, whether from a compact disk-like cloud or through later rearrangements and scattering. By studying these outer planets, researchers also refine techniques for detecting similar cold red worlds around other stars. Each signal from Proxima C or Proxima D becomes both a local detail and a template for distant systems. As the narrative flows onward, the gaze shifts from these wide, cold orbits toward the more delicate structures of dust and debris that fill the spaces between. Their tiny grains and fragments quietly record the collisions and migrations that have shaped Proxima Centauri's family of red worlds over billions of years. Proxima Centauri's planetary system is not only made of planets, it is also threaded with bands of dust and small bodies that move quietly through the red star's faint light. The guiding idea here is simple. Between and beyond the main orbits, countless fragments record the system's history in tiny drifting pieces. Dust in a planetary system consists of grains left over from planet formation or created by later collisions. Each grain is a speck of rock or ice, sometimes no larger than smoke particles circling the star on a gentle path. Over time, collisions between larger bodies called planetesimals grind material down, feeding these belts with fresh fragments. In the Proxima system, such dust appears to gather in one or more zones, forming structures that echo the asteroid and distant ice belts of the solar system on a smaller scale. Around the nearest star beyond the Sun, there is more than empty space between orbits. There is a faint, dusty architecture. These belts behave like a kind of soft fossil record. Their distribution tells where collisions have been frequent, where small bodies still cluster, and where planets may have stirred the disk with their gravity. When a planet moves through a field of planetesimals, its pull can concentrate or scatter them, sculpting gaps, clumps, or arcs. Over millions of years, the result is a subtle pattern in which dust traces the invisible lines of gravitational influence. A quiet payoff emerges. Even without seeing every planet directly, the shapes of dust belts hint at hidden companions. For Proxima's dust, the red dwarf's small mass plays an important role. Radiation pressure, the push from starlight on tiny grains, is weaker than it would be around a brighter star. As a result, fine dust is not blown away as quickly. Grains can survive longer on their orbits, gradually spiraling inward under the combined effects of stellar wind and drag from their own faint interactions with light. The system becomes a slow conveyor belt of material carrying fragments from the cold outskirts toward the warmer inner regions. A main metaphor for this section is a quiet, circular river of powder flowing around a central ember. Within that flow, some grains spiral gently into the star while others collide and merge into slightly larger bodies. Occasionally a fragment may be perturbed by a planet and flung into a new orbit, turning one smooth band into a more complex web. From far away, these dusty structures remain invisible to ordinary sight. Instead, they reveal themselves through the faint glow of their own warmth at long wavelengths. cold dust absorbs a portion of the star's light and re-emits it in the form of gentle millimeter or infrared radiation. In that way, an unseen ring of grains circling Proxima becomes a measurable halo of cold brightness. For Proxima Centauri, early studies hint at more than one zone of dust. An inner belt may lie relatively close to the star, while an outer belt extends much farther away, perhaps comparable in scale to the solar system's distant ice region. If so, then the nearest stellar neighbour hosts not just a compact inner system, but also a wide, cold reservoir of material on its outskirts. Around that reservoir, small icy bodies would drift on slow, long orbits, occasionally colliding and sending fresh dust inward. A secondary visual anchor brings this to the mind's eye. Picture a dark, spacious room with a dim red lamp at the centre, and a fine mist of powder suspended in wide rings around it, glowing faintly where the light catches each particle. For astronomers, Proxima's dust belts matter because they complete the story of how the system formed and evolved. Dust traces the leftover building blocks that once took part in forming planets, and that continue to reshape the system through quiet impacts. By measuring how much dust exists, how cold it is, and how it is distributed, it becomes possible to test models of the system's age and past events. A relatively dense belt might signal recent collisions or an active population of small bodies. A thinner one might reflect an older, calmer stage. In gentle terms, the dust around Proxima is a record of both violence and rest. Nearby worlds sit within or adjacent to this record, crossing planes lined with fragments as they complete their orbits. Occasionally, individual grains or small rocks may fall inward and meet a planet's atmosphere, creating faint meteors that scratch quick lines of light across red-lit skies. Whether or not any observer ever watches such streaks, they would mark the ongoing exchange between belts, planets, and star. As the journey continues, attention turns from these diffuse dusty structures to the way light and shadow themselves behave near a red dwarf. The next step is to pause on the colours, brightness and slow sunrises that would define the look and rhythm of days and nights in Proxima's realm. Proxima Centauri's light is soft red and strangely gentle, yet it shapes every detail of how days and nights unfold on its worlds. Colours, shadows, and the pace of sunrise and sunset all slow down and deepen under this small red star. Near Proxima, brightness never reaches the fierce glare of a sun-like star, so landscapes live mostly in long twilights and muted tones. A red dwarf has a cooler surface than a star like the sun, so most of its visible light comes out in deep reds and oranges, with much of its energy in infrared wavelengths that eyes cannot see. On a rocky world in the habitable zone, the star would appear larger in the sky than the sun does from Earth, yet its glow would remain softer. At local noon on the day side, the ground would lie beneath a warm coppery light, bright enough to cast shadows, but not harsh. Rock, soil, and any plant-like forms would reflect this light as dark reds, browns, and muted golds. Ice and snow, if present, would not shine in stark white. Instead, they would blush slightly pink like frost lit by embers. Under Proxima's light, familiar materials look unfamiliar, not because they change, but because the star that illuminates them speaks a different colour language. Shadows around a red dwarf also behave in a distinctive way. Because the star is faint, the contrast between lit areas and shade stays strong even at midday. On a close-in planet, tall cliffs or boulders would throw long, deep shadows that remain cool and softly coloured. Within those shadows, only red light scattered from the sky, and nearby surfaces would filter in, creating pockets of dimness, where shapes blur and edges soften. Farther from the substellar point where the star stands lower in the sky, light would pass through more atmosphere and lose some of its remaining brightness. This deepens the sense that even daytime under Proxima is close to twilight. The main metaphor for this section is simple. Light near Proxima paints everything as if the universe were lit by a single patient campfire, never flaring into dazzling noon, never fading completely while the star is above the horizon. On a tidally locked world, the pace of sunrise and sunset changes as well. Along the terminator where day and night meet, the star would hang near the horizon and drift very slowly. The line between light and darkness does not race across the surface each day. Instead, it creeps, adjusting only as orbital motion, and any slight tilt of the planet shifts the geometry. For an observer fixed on that twilight ring, the red sun might seem frozen at one low angle, its disk slightly blurred by the atmosphere, its glow constant. High in the air, thin clouds would catch this low-angle light and spread it into broad pale streaks, turning the sky into layers of crimson rust and soft purple. On a rotating world not locked to the star, days and nights would still cycle, but the transitions would linger. Because the star is dim, dawn would begin as a barely noticeable brightening of the deep night sky. A faint red ember would rise, thickening into a disk that slowly strengthens the light. Shadows would grow shorter with great patience, and colours would emerge gradually from darkness. At evening the sequence would reverse, with colours cooling and shadows lengthening for a long time before true night returns. Imagine a countryside where the hour of golden light before sunset stretches into half a day, bathing hills, plains and oceans in a steady, subdued glow. The interaction between Proxima's spectrum and any atmosphere deepens these effects. Gases and small particles in the air would scatter blue light more efficiently, but there is little blue in the star's output, so the sky might rarely reach a clear, bright hue. Instead, it could settle into shades of dark salmon, hazy violet, or deep grey, depending on clouds and fine dust. During powerful flares, the visible brightness could spike, making the star briefly sharper and whiter, but the dominant impression would still be red. As flares fade, the light would slide back into its usual muted state, like a fire returning from a sudden gust to a steady burn. For climate and daily rhythm on any such world, these slow, gentle shifts in light matter. They control how quickly surfaces heat and cool, how thick fogs form in low valleys, and how deeply light penetrates oceans. Proxima's light defines not only what can be seen, but also how time feels. A day under a red dwarf is less a sequence of sharp events and more a continuous quiet gradient between shades of dimness. As the journey moves onward, attention turns from these visible effects of light and shadow to the distant instruments that study Proxima itself. The next step is to leave imagined skies and return to the vantage point of telescopes, where subtle changes in brightness and colour reveal the presence of these red worlds from light years away. Proxima Centauri sits so far away that even its nearest planets remain tiny unresolved points in any telescope. This section lingers on what can actually be measured from that distance, and how much must still be left to careful inference. The gentle insight here is that almost everything known about Proxima's worlds comes from patterns in light, not from pictures. A telescope is at heart a device that gathers light from a distant object and separates that light into position, brightness and colour. For Proxima, the star is bright enough to measure as a single red point, while the planets stay hidden in its glare. Their presence appears indirectly through repeated changes in the star's motion and subtle variations in its light. Radial velocity is one key method for finding these changes. Radial velocity means the component of motion toward or away from the observer. As a planet orbits, its gravity pulls gently on the star, causing the star to wobble along the line of sight. That wobble shifts the star's spectrum, the pattern of colours in its light, in a tiny back and forth way. By watching Proxima's spectrum over many years, observatories detect regular shifts that reveal the presence of planets and suggest their orbital periods and minimum masses. The first quiet payoff appears here. Proxima B, C and D emerge not as seen worlds, but as repeating notes in the star's measured motion. A second method looks for small dips in brightness. A transit is when a planet passes in front of its star and blocks a tiny fraction of the star's light. Transit searches monitor Proxima over long stretches, measuring brightness again and again to catch any regular dimming. So far, evidence for transits around Proxima remains uncertain, yet the method sets strict limits. If a planet as large as some hot close-in world seen elsewhere crossed the star, the event would stand out. Its absence suggests that either the orbits are tilted away from the line of sight, or the planets are too small to produce an obvious signal. Even a non-detection becomes a piece of information quietly shaping knowledge of the system's geometry. Spectroscopy, the study of how light spreads into different colours, also plays a central role. Spectroscopy is the measurement of intensity as a function of wavelength. For Proxima spectra show the star's temperature composition and activity level. Strong lines in the spectrum shift as the star moves, adding detail to radial velocity work. In principle, if a planet's atmosphere ever produces a detectable signal, careful spectroscopy during a transit could reveal hints of gas types and temperatures. At Proxima's distance and current instrument sensitivity, such atmospheric studies remain a hope rather than an established result, but the method is ready for the future. Interferometers and high-resolution imaging systems contribute another layer of information. An interferometer links the light from more than one telescope to imitate a much larger mirror. With this technique, astronomers can sharpen their view of the region around Proxima, searching for any faint companions or extended structures in dust. Directly imaging the planets themselves is still beyond reach. The contrast between star and planet is extreme, and the angle between them on the sky is tiny. Yet even partial success in separating starlight from nearby dust gives clues to the structure of belts and possible outer bodies. Millimeter and radio observatories extend this idea by mapping the cool glow of dust around the star, turning invisible grains into a faint measurable ring. Astrometry offers another path. Astrometry is the precise tracking of a star's position on the sky. As Proxima's planets tug on it, the star follows a small wandering path against the distant background. Very sensitive instruments can detect this motion and confirm planet masses and orbits from a different angle than radial velocity. Together, these methods weave a web of constraints. No single measurement tells the full story, but each one narrows the range of what the planets can be. From this distance, no mountains, clouds, or oceans appear directly, only the combined pull they exert on their star and the light they slightly modify. A soft visual image ties this together. From Earth, Proxima and its worlds resemble a distant orchestra heard through a wall where only certain notes carry. Radial velocity, transit spectra, and positional shifts are those notes. By listening carefully over many years, observatories separate noise from pattern and build a quiet musical sketch of the system. The key lesson is that current telescopes already reach across the 4 light-year gap with remarkable sensitivity, yet they still deliver only indirect impressions. It is a science of patient listening and comparison rather than vivid close-ups, a style well matched to the slow, enduring nature of red worlds. As the narrative moves on, attention turns toward ideas for future instruments and interstellar probes that might sharpen this view. Those concepts promise to turn today's delicate hints into more direct encounters with the nearest red worlds. Proxima Centauri has been studied for decades from afar, yet it remains only a point of light in even the largest telescopes. This section turns from those distant measurements to quiet ideas for visiting its system more directly with machines. The gentle insight is that the nearest star beyond the Sun is both reachable and demanding. Any probe sent there must travel for years or centuries, then work largely on its own when it arrives. Interstellar spaceflight is simply travel between stars over distances measured in light years. At present, the fastest spacecraft launched from the solar system would still need tens of thousands of years to reach Proxima Centauri. Concepts for future missions try to shorten that journey to something closer to a human lifetime or a few human generations. One family of ideas uses light itself as the driving force. In these concepts, a powerful laser array based near the Sun shines on a thin reflective sail attached to a very small probe. The sail catches the stream of photons and is pushed forward much as a traditional sail is pushed by wind. Because the probe can be extremely light, perhaps no heavier than a handful of coins, the push from light alone might accelerate it quickly. At high speed, it could reach a noticeable fraction of the speed of light. At such speeds, the crossing to Proxima could take only decades rather than millennia, though still far longer than any ordinary mission within the solar system. A quiet image forms of a swarm of tiny shining seeds flung outward by beams of light coasting into the dark between stars. Another family of concepts imagines larger, heavier craft driven by more massive engines. Some designs use fusion, the same process that powers stars to heat propellant and push the craft forward with high efficiency. Others use beams of microwaves or particle streams from near the solar system to push a reflector on the spacecraft without carrying much fuel. These vehicles would travel more slowly than the light sail seeds, but could carry more instruments and perhaps small landers. Their journeys might last centuries, turning them into moving observatories that quietly record the changing view as they leave the Sun and approach Proxima. In all these plans, communication delay plays an important role. A signal from Proxima takes more than 4 years to reach Earth, and any reply takes another 4. This means a probe near the star cannot wait for instructions about every decision. It must carry a degree of autonomy, the ability to make careful choices based on local conditions and general guidelines. On-board redundant systems, self-repair routines, and long sleep cycles would help the craft endure long stretches of silence and radiation. The main challenge is not only to arrive, but to survive long enough to observe and send its findings home. Dust and tiny rocks in interstellar space introduce another quiet hazard. At a small fraction of light speed, even a grain of dust can hit with great energy. To reduce this risk, proposed probes use narrow profiles, thin shields or leading clouds of particles to sweep the path ahead. Over decades of flight, these measures may mean the difference between a working instrument and a silent fragment. Despite such dangers, the reward is vivid. A probe passing through the Proxima system would see the red dwarf as a disk, not a point. It could watch the planets grow from dots into crescents and disks, resolving cloud bands, ice caps, or dark lava plains if such features exist. Instruments could feel the stellar wind, directly map magnetic fields, and taste atmospheric gases during a close flyby. In that moment, 4 light-years of inference would become a set of local physical measurements. Yet even this encounter would have limits. High speeds make it hard to slow down, so many designs accept a brief flyby instead of a long orbit. The probe would rush through the system in days or weeks, collecting as much data as possible before fading back into deep space. Years later, its stored observations would drift home as a stream of signals across the void. For the people receiving them, the probe's close passage would already belong to the past. Viewed in this quiet way, future missions to Proxima Centauri are extensions of the same careful listening that telescopes already perform. They reach farther, move longer, and bring the vantage point closer to the red worlds. Yet they still face distance as a patient adversary, rather than an enemy to be conquered. As the narrative nears its end, attention gently returns from these imagined journeys to a more reflective view. The final step is to rest at the boundary between what such missions could reveal. Some details of Proxima's red worlds may always remain beyond direct reach. Proxima Centauri now stands at the edge of what can be known in detail and what must remain softly out of reach. This final step pauses at that boundary and looks back across the path from the solar system to the nearest red worlds. The main idea is calm and simple. Even when a star lies only a little more than 4 light years away, much of its story is told in shadows, echoes, and careful patterns rather than clear images. Telescopes measure motions, brightness, and colors, building models of planets, dust belts, and flares, but the exact look and feel of those landscapes stays hidden. A plain sentence crystallizes this. There is a difference between knowing that a world exists and seeing its surface as it truly is. In Proxima's case, that difference becomes the quiet space where imagination and measured science meet. From Earth's vantage point, Proxima and its planets remain no more than shifting points in data streams. Each point represents a night of observations under a distant sky. Over years, these signals fold together into a picture of a compact system rich in structure, yet still lacking direct views. The result is a kind of cosmic silhouette. Planets' belts and winds are outlined, but their finer details dissolve into uncertainty. A gentle visual anchor helps. It is like standing on a dark shore and watching a cluster of lights across a wide bay. There is an understanding that homes and streets lie there, and an acceptance that individual faces remain unseen. Proxima's red worlds occupy that distant shore in the mind. Many questions that draw curiosity toward them may never receive sharp answers. Proxima b may carry a thick atmosphere or only a thin veil. Oceans may have once covered parts of its surface and later vanished into ice and rock. Chemistry in sheltered regions may climb toward greater complexity or stay simple, and all of these possibilities may remain unresolved. Even a fast flyby probe would see only a brief phase in a long planetary history. The possibility of life, often the first question asked of any new world, may be the last to yield information if it yields it at all. A calm conclusion follows. The nearest potentially temperate exoplanet is also a reminder that proximity does not guarantee complete understanding. Yet this limit is not a failure. It is a natural part of astronomy where many systems across the galaxy can never be visited directly. Proxima Centauri simply makes that limitation clearer because it stands so close. By learning how much can be drawn from light alone, researchers refine tools that can be applied to countless other red dwarfs and their planets. In that way, every uncertainty at Proxima becomes a guide to how to handle uncertainty elsewhere. Red dwarfs are the most common stars in the galaxy, and Proxima is a single vivid example. Its flares, winds, dust belts, and compact planetary system all point to patterns likely repeated many times around other faint suns. The study of this one nearby red star therefore reaches far beyond its own planets. It hints at how many red worlds may exist, and how often they might keep their air. A gentle second metaphor offers itself. Proxima is like a small, well-examined leaf pressed against the immense forest of the Milky Way, giving a sense of its texture without revealing every tree. On a more personal scale, the limit of observation around Proxima also has a settling effect. It shows that not every mystery must be fully solved to be meaningful. Knowing that there is a compact system of red worlds in the very next stellar neighborhood is already enough to shift ideas of place. The sun no longer feels alone. It becomes one light among many in a network of possible planetary families. The thought that other skies exist, lit by small red suns and framed by slow, deep twilights, can be quietly reassuring. It suggests that the universe holds variety without hurry. Proxima Centauri will continue to burn for trillions of years long after the sun has changed into a different kind of object. Its planets, whatever their precise nature, will keep circling in the dark, tracing their orbits through the faint glow of dust and the soft pressure of stellar wind. Instruments on and around Earth will keep listening for new clues, refining masses' orbits and activity cycles as technology improves. Yet some aspects of these red worlds will always remain matters of inference rather than direct sight. The closing insight is gentle. At the boundary of what can be measured around Proxima Centauri, a quiet balance forms between knowledge and mystery. That balance allows curiosity to stay awake while the mind rests. With the nearest red star and its worlds placed in this perspective, the night sky becomes less an unknown expanse and more a calm, spacious neighborhood. In that neighborhood, distant points of light hint at stories that unfold slowly far beyond a single lifetime. The journey to Proxima Centauri now settles into quiet memory. A small red star, its compact family of worlds, and the soft glow of dust and distant flares all drift into a calm, distant backdrop. The key shapes are already in place. There is a nearby red sun that burns slowly planets that circle close or wander farther out, and a soft boundary where knowledge fades into gentle uncertainty. The mind no longer needs to hold every detail. The idea of Proxima as a long-lived ember in the local galaxy is enough. Images of red-lit skies, slow sunrises, and narrow twilight bands around tidally locked worlds can simply float light and unhurried without needing answers. Thoughts of atmospheres, winds, and dust belts can fade into a broader sense that many different kinds of worlds exist, most of them quiet and unknown. The pace that once followed orbits, flares, and future probes can now slow to match the star's own patience. In this slower rhythm, the 4 light years between the Sun and Proxima become less a challenge and more a soft stretch of space that connects one neighborhood of stars to another. The solar system feels gently linked to its nearest red neighbor, not by spacecraft, but by shared patterns of gravity and light. That link can rest, now held as a simple awareness that the night sky is inhabited by more than empty points. Proxima and its red worlds can fade into the background of thought, like distant lamps along a very wide shore, steady and unthreatening. Breathing can follow that same pattern, moving in and out, without effort, like slow orbits continuing in the dark. With the nearest star beyond the sun placed quietly in its corner of the mind, the rest of the sky can close around it in a soft, familiar darkness.